Hey everyone, this is going to be a very long video, and in this video we are tackling the important subjects of thermal energy and its kind of cousin, heat. These are super important concepts in physics and for this unit, and I'm going to take a lot of time to make sure I explain everything as best as I can. There'll be timestamps in the video description, so if you just need a specific topic of this video, you can jump straight to it. Before we start, I'm going to get one kind of basic concept out of the way, and that is how we are going to measure temperature. Most of you are probably used to measuring temperature in one of two ways, and that's in degrees Celsius or degrees Fahrenheit. And these are both okay ways to measure temperature. In Canada, most of the time we use Celsius, and all scientists the world over use Celsius. One of the primary ways we're going to be measuring temperature in this unit is with Celsius. In Celsius, we have a scale that essentially goes from 0 to 100, where 0 and 100 are the endpoints. Obviously, you can have negative and greater than 100. 0 is the freezing point of water, and 100 is the boiling point of water. You're familiar with this. You probably use Celsius on a day-to-day basis. However, there is another scale that is only used in science, and it is kelvins. Notice it's not degrees Kelvin. There's no degree. The unit is just called a Kelvin, like this. And the unit of a Kelvin has a similar scale to Celsius and is related to Celsius by a very simple metric. To convert Celsius to Kelvin, you add 273 degrees. So, 0 degrees Celsius is 273 degrees Kelvin, but you don't say degrees Kelvin, it's just 273 Kelvin. Why 273? Because negative 273 degrees Celsius, technically there's a decimal there, but we usually round, is this value called absolute zero. And absolute zero is the coldest possible temperature in the universe, because at absolute zero, all molecules, all life on Earth stops moving. Remember in our last video we learned about how atoms and particles are moving around in substances. At absolute zero, everything stops. It freezes, no life can be sustained. It literally is the coldest and the most absolute temperature we can get. Kelvin is based on that. 0 degrees Kelvin, or 0 Kelvin, is absolute zero. It literally is the most absolute number, and we measure up from that. You're not going to see Kelvin a ton today, but you might in the future, so it's good to understand the differences between Celsius and Kelvin and how to convert. Remember that magic number, 273. Alright, we can finally start with the main topic of today, which is thermal energy and heat. And we're going to compare them, and also a third concept, temperature. These three concepts, thermal energy, heat, and temperature, are probably the most important things to get away from this video. Now, we're going to start with a basic fact, and that is in any substance that we deal with in the world, think of anything. Pick an object in your room in front of you, like a book, and you'll note that inside that object there's a lot of particles. We learned about this last time in the kinetic molecular theory of matter. And it's important to note that there is both kinetic and potential energy in every substance. Remember how we talked a lot in our energy unit about the difference between kinetic and potential energy, using an analogy of the rock that's rolling down the hill. Potential energy is that energy that's like ready to act, but it hasn't acted yet. And once it acts and we get motion, we get kinetic energy. Well, every substance at a molecular level has kinetic energy and potential energy. We call this the internal energy of the object because you can't see the effects of it at all. It's in the particles, in the molecules, inside this substance. And every single substance has both kinetic energy and potential energy. Kinetic energy is things like the vibrations of particles, the rotations of particles, motion of particles through the substance, which happens constantly and randomly. And potential energy is things like the forces between bonds and the forces of attraction, and even the elastic behavior of these vibrations. You don't need to know the details, but the point is that there is both kinetic energy and potential energy in every substance in the universe. This becomes important because we're now going to define these three terms: thermal energy, heat, and temperature. And you're going to want to know these definitions. We define temperature as the average kinetic energy of particles in a substance. It's the average kinetic energy of the particles in a substance. Of particles. And I'm not going to say in a substance. That kind of, we could assume that. So what this means is if you took the kinetic energy of every particle in that substance, theoretically, not that you could actually measure that in any way, and averaged them out, you would get the temperature. And we measure that, obviously, in units called degrees Celsius, sometimes degrees Fahrenheit, or Kelvin, which is the one we just learned about. So temperature, we have our own intuitive notion of temperature. Oh, this is hot, this is cold, it's a nice day out. However, the precise physics definition of temperature is the average kinetic energy of particles. Take all the particles, get the amount of kinetic energy, average it out. You got temperature. Thermal energy is the total kinetic and potential energy. It's kinetic and potential energy of the particles. So this is a different metric. We would take every single particle, theoretically again, and get all the kinetic and the potential energy of each particle and add them all together. And when we add them all together, we'll get the thermal energy of that object. Now, one thing that's important to understand about thermal energy is that the greater the mass of the object, there's more thermal energy. And this is kind of important to understand because the more mass an object has, the more particles are in it. And the more particles, you get more particle motion, and so more particle kinetic energy, and you get more particle bonds, so you get more particle potential energy. So greater mass, greater thermal energy. And finally, we have the concept of heat. And heat is related to thermal energy because it's the energy, the thermal energy, transferred. And it's the energy transferred typically from one object to another, and always from warm to cool. This is very important. Heat always transfers from a warm object to a cool object. You can never have temperature or thermal energy transfer in the reverse direction. Things do not go from a cool object to a hot object. It will not happen. The laws of the universe say warm to cool. Heat it actually has a symbol, and that symbol is Q, and it stands for quantity of heat. And we are going to deal with Q quite a bit in this unit. And heat is measured in joules because, like the other energies we've looked at so far, it is an energy quantity. We can also make this kind of conclusion. We already know this formula. Remember how work equaled the change in energy, and we were dealing with mechanical energy? Well, we have a similar formula in thermal energy, and it's that Q, which is that heat, equals the change in thermal energy. And this is super important because this is how we're going to look at this unit. Remember that heat is the change in thermal energy. So there's thermal energy, the total kinetic and potential energy of these particles, and there's heat, which is the energy transferred between a warm object to a cool object. And these are kind of interrelated, and then alongside it we have temperature. And the reason temperature is useful, it's the way we quantifiably measure this other stuff. We are able to actually physically use a thermometer and get the temperature of a substance. Okay, next topic here. The types of heat transfer. Heat transfer. We just talked about the concept of heat and how its basic thing is that it transfers always from a warm substance to a cool substance. Every time, always like this. Heat transfer itself can happen by 3 different mechanisms. And the 3 mechanisms are called conduction, convection, and radiation. And you've probably heard every one of these words, but probably in different different contexts than this. Conduction, you might have heard in the context of electricity that conducts. And that's probably a familiar concept to you. Heat conduction works very similar. Convection, you've probably heard maybe that you have a convection oven at home. Your oven probably operates by convection, and I'll explain what that is. And radiation you've probably heard of maybe in the context of Chernobyl or some other form of nuclear apocalypse. Radiation is the third type of heat transfer. I'm going to explain what each of these does. Conduction operates by direct molecular collision. That means, literally, you have a high-speed particle. Here's a high-speed particle. It's zooming around really fast. Vroom, vroom, vroom. And the high-speed particle is going to hit, it's going to go vroom, into this slower particle. And when it hits the slower particle, just like how balls work in normal life, like billiard balls when you're playing pool, for instance, if you have a fast ball and it's hitting that slower ball is going to get speed, and now it's going to go faster. So what you've just done is you've taken a high-speed particle, hit it into a slow-speed particle, and that lower-speeded particle is now a higher-speed particle. So you've overall increased the kinetic energy of that second particle. And that is a transfer of heat, because higher speed is higher heat, if you remember from our last video. So here is your warm substance, and here is your cool substance, and they've just gotten some of the heat from the other substance. That cool substance has gained heat from the warm substance. For conduction to occur, you need physical contact. This is the most important thing to get out of this. Conduction cannot happen without the physical contact of the two substances. Okay. Next up, we have convection. Convection operates with liquids, gases, and kind of fluids. When a fluid is heated, and then it travels away, it carries the thermal energy with it. And it'll carry the thermal energy with it, and you'll get this thing called a convection current. Because, and you may have heard this before, hot air, and this also applies within liquids, rises. Hot air rises, and cold air falls. And so you get this thing where the hot air is rising, it's going, and then you're getting the cold air falling. And you create this convection current. Look, you're getting kind of this loop of moving, circulating air. And this also applies in liquids. This is how your convection oven works. It provides heat to the air in the oven, and it's the actual current that moves the air in the oven. It circulates. You provide it with some hot air. That hot air rises. It slowly cools. It funnels downwards. That cool air goes back into the heater and heats up again, and you get a cycle of reheating air that keeps the inside of the oven very uniformly hot. And that's how convection cooking works. This is called a convection current. Notice that convection, unlike conduction, operates without physical contact, just by liquids or gases that are moving around in these currents. Finally, we have radiation. Radiation has to do with electromagnetic waves, which we're going to learn about in the future, but basically it's the random movement of atoms and molecules will actually radiate thermal energy kind of outside of the object. Every object in the world, believe it or not, has some amount of radiation. And we usually hear about radiation like it's a bad thing. Like, that sample of uranium has a lot of radiation. I wouldn't go near it. But radiation occurs in every single object. The bed you sleep in, the food you eat, all has radiation. The problem, or the good thing, is that not a lot of radiation is dangerous. Only some types. But radiation at the end of the day is just a hot object radiating or releasing some energy spontaneously into the colder surroundings. So here's your hot object, and it's really just releasing energy into its surroundings, and those surroundings would theoretically be cooler. And that's how radiation operates. The sun is one of the biggest uses of radiation, or examples of radiation, and we harness the sun's energy in solar panels, that thermal energy that the sun releases. In fact, without the radiation from the sun, that thermal radiation, Earth would be dead and cold, because the sun's thermal energy that it transfers to the Earth is really how we live. So now we've learned about two concepts here. We've learned about thermal energy, heat, and temperature, how they're related, what they mean, and we've learned about heat transfer, which is from warm to cool, and the three mechanisms: conduction, convection, and radiation. Concept 3 is the concept of heat capacity. Heat capacity. Heat capacity is an interesting concept. Basically, it's referring to the capacity or the ability of an object to to absorb or release energy. So if you have an object, it has this innate ability to absorb energy or to release it. And that amount, which we measure with like a quantifiable number, is called the heat capacity. There's a lot of science that goes into determining the heat capacity of things, and we don't have to worry about any of it because on our tests and for our purposes, we are going to have a chart which gives you the specific amount of heat capacity for certain objects. Now, heat capacity in general is a very generic concept. It's just like the ability to absorb or release energy. Absorb or release energy. And specifically, thermal energy is what we're talking about here. And this is a very general topic. There's not a lot that's specific about this, which is why we have literally something called the specific heat capacity. Specific heat capacity. And the specific heat capacity is a concrete number, and it's the amount of heat energy needed to raise the temperature. You need to raise the temperature of 1 kilogram of a substance by 1 degree Celsius. You don't really need to know this, but I'm providing it there in case you care. It's measured in this unit, which is complicated, I admit, and this unit is joule kilograms degrees Celsius, which has a bunch of components. There's a component of energy, the joules, a component of mass, and a component of temperature. Component of energy, a component of mass, and a component of temperature. And this together gets you the specific heat capacity, which we indicate as the letter C. C for capacity. This is the specific heat capacity. And you'll get numbers thrown at you, like, oh, the heat capacity of some substance is like, I'm picking a random number here, 3.2 times 10 to the 3 joule kilogram degrees Celsius. You might find out. And for us, we're going to have a table of these, which literally tells us for certain materials, here are the heat capacities we need to worry about. And that's what the heat capacity is. Why would you ever care about the heat capacity of an object? Because of the last and most important topic in this unit, or in this, video, and that is going back to here. We talked about heat and the energy transferred. And we talked about this quantity called Q, which is a measure of heat. It's the quantity of heat. Well, Q is a pretty important thing. Q is a measure of quantity of heat, like I said, which is literally the amount of heat, and that's all quantity means. And the variable Q is what we use, and it's the total amount of thermal energy which is transferred from warm to cool. From that warm substance to the cool substance, a total amount of thermal energy gets transferred over. That's kind of the principle of this. And the amount that physically gets transferred is Q. Remember, Q is the change in thermal energy. It's that transfer of thermal energy. And it has a formula. This formula looks like this. This is the most important thing, I would argue, in this lesson, besides the fact that warm goes to cool. And that is that Q equals mc delta T. And mc delta T is 3 components here. The m is the mass of the object that we're talking about. The C is that heat capacity that we were just dealing with, which you would have to know the substance of that mass. If the mass is a mass of water, then you need the heat capacity of water. If it's a mass of silver, you need the heat capacity of silver. And delta T is change in temperature. Capital T is temperature, little t is time. Don't get those confused. The change in temperature, literally T2 minus T1. And so when you multiply these 3 quantities together, the mass, the heat capacity, the change in temperature, you get this magical value Q, which is very important because it tells us the amount of thermal energy which is transferred from a warmer substance to a colder substance. Now, I gave you a lot of kind of abstract information in this video. We talked about thermal energy, heat, temperature, heat transfer, warm to cool, conduction, convection, radiation, the quantity of heat, We talked about heat capacity and specific heat capacity. I threw a new formula at you, Q equals mc delta T. There's a lot here. So I want to summarize basically by telling you to kind of go over these concepts, understand the basics of how they work, and then realize that in the next video, we're going to talk about an important concept that will start to kind of make this all make more sense. It will allow you to realize why you would want to use these in a practical sense. Because we're going to start dealing with different objects and how they interact with regards to thermal energy. But for now, this is all for this video. Hopefully this was helpful, and thanks for watching.